Today we'll be covering the topic of asynchronous design and how it applies to CPUs. In particular, this presentation will cover some of the problems with synchronous and clocked designs, and then we'll provide an overview of how asynchronous circuits work, and then we'll discuss the advantages and disadvantages of asynchronous CPUs and whether it's worth using. Finally, we'll provide some examples of current applications for asynchronous design and the future applications. First, some problems with synchronous design. Synchronous circuits generally have been favored in CPU design for the fact that they are easier to design, easier to test and debug. Their operation is more widely understood in the industry than asynchronous circuits, and the timing of the clock period makes it easier to regulate data flow, easier to control and predict when data gets transmitted between components. However, the synchronous approach is not without its share of drawbacks. For starters, we are forced to measure performance based on the worst-case execution. Since all components are tied together, the speed of execution cannot go faster than the slowest component. We have to make the period of the clock long enough to account for all propagation delays, as has been extensively covered this semester, and allow all output to be stable before the next clock pulse occurs. Performance is greatly dependent on the length of the critical path, meaning performance can't improve beyond a certain point, regardless if the data path actually uses the full critical path or not. So that means there is a lot of time the circuit sits idle, waiting for the next clock pulse, and this results in wasted time and performance potential. The other major setback is the issue of power and heat. Since power equals heat, there is a limit to how fast we can make the clock speed go before heat becomes an issue. Running a continuous clock and a widely distributed clock signal takes a lot of power, as the clock is continuously ticking for the entire time the system is on, regardless of whether a particular circuit is actually receiving inputs or not. It's still drawing power because the clock is connected to it. And since components of a synchronous circuit are tied together to the clock, this means that to some degree all components are active. Components, active or inactive, are continuously drawing power. So what solutions are available to the drawback of synchronous CPUs? Most of the problems are a result of the clock, so the obvious solution is to get rid of the clock. And this is one major area of research for improving CPU design, is that of removing the clock altogether and having a clockless CPU. There have been decades of research poured into this very topic using asynchronous design. However, the biggest hurdle to overcoming this use of a clockless design is how to synchronize data flow between components of the CPU without a globally distributed clock signal to regulate it. More on that in a bit. Before we delve into the specifics of asynchronous CPUs, I first want to provide a brief overview of how asynchronous circuits work. Asynchronous circuits are not governed by a clock signal. That is to say, data transmits when it is ready to go instead of waiting for the clock pulse to tell it to do so. Since components do not have to wait for a clock pulse, a computation step can be started immediately after the last step is finished, meaning we no longer time the circuit based on a worst-case scenario basis. Instead, performance is measured on an average-case scenario basis. As a basic comparison, we have this diagram where we see some arbitrary combinatorial logic hooked up in both an asynchronous and synchronous manner. For the synchronous logic to work properly, the states are stored in some register, and they wait for the clock pulse to send it off as the current state for the combinatorial logic. However, in the asynchronous setup above, the clock and register are bypassed by sending the next state output directly into the current state input, and the next step of combinatorial logic begins immediately as this change in input occurs. And this brings us to the hurdle I mentioned earlier. That is, how do we synchronize this without a clock? There is a situation known as a race condition that can occur without the presence of a clock that we must account for. That is, what happens when values of one circuit or component arrive at the inputs of another circuit or component incorrectly and or out of sequence. The issue we get without a clock is that whichever signal gets to a gate or input first is what gets used, even if it results in an undesirable outcome. If transitions on two inputs arrive at almost the same time, there is the potential to send the circuit into the wrong state, which we don't want. And that is the purpose of the clock in asynchronous design, is to handle that exact situation. So how do we handle this in an asynchronous circuit without a clock? The best solution is to open a sort of communication channel in the circuit using two wires. One wire to send the bits of data, while the second one is used to send what are referred to as handshake signals to indicate when work has been completed and when the bits on the first wire should actually be used. This whole process is referred to as the handshake interface, which is how asynchronous circuits synchronize data without a clock. So let's take a look at what that looks like. Here's a diagram to illustrate the handshake interface. These bubbly cloud things represent components of the circuit that need to communicate and send data with each other, which is illustrated by this big fat arrow right here. When A has data that it's ready to send, it will transmit a signal to basically state that I have data. However, B isn't going to really do anything with it until it's ready to accept the data, in which it will transmit an I'm ready signal. If that was confusing, here's another illustration I have. This illustrates the two-phase protocol of asynchronous communication. And how it works is that the sender here ensures that all bits of data are valid prior to sending a request event to the receiver. The receiver accepts the data prior to sending an acknowledgement event, which permits the sender to remove the old data and place new values on the data lines. And this diagram down here shows how this process looks over time. So if you aren't totally lost, let's move on to some advantages that employing asynchronous design to CPU comes with. First and foremost, being that asynchronous CPUs come with a higher performance in general. Without a global clock, a computational step can be started immediately after the last step is finished, as opposed to waiting for the next clock pulse, like in a synchronous CPU. As an example, this means that arithmetic instructions will compute much faster since they're not running on the same time frame that would be required to allow a load or store instruction to compute accurately. Additionally, power use is also decreased since we don't have to account for the clock continuously pulsing for the entire time that the system is up and running. Only active functional units consume power, while inactive units remain in a standby mode. This means that we aren't wasting power on units of the CPU that aren't being used versus having the clock signal being fed to them and present every time and everywhere in the synchronous design. Another application is improved noise on power supply lines. The presence of the clock can generate electromagnetic interference at its clock frequency. The clock modulates the overall supply current, causing peaks in power supply noise and electromagnetic emission to occur at the clock frequency. So obviously removing the clock will see an improvement in this regard.
With all the apparent advantages to asynchronous design, and the fact that asynchronous circuitry has been around since 1989 and the idea for it has been around since the 1950s, it begs the question, why is this technology not more prominent in the world today? One of the disadvantages to asynchronous circuitry is that it turns out the improved performance talked about isn't quite as improved as originally thought. This can be due to the overhead that is required for asynchronous circuitry. The overhead may be up to double the number of circuit elements due to completion detection and design for test circuits. Essentially, the design for test circuits are required for debugging, and the completion detection, so in essence the handshake, requires additional circuit elements. So when combined with the fact that synchronous circuits have been getting improved performance over the last couple of years due to pipelining and retiming of their clocks, the actual improved performance over synchronous design is not as large as originally thought. Asynchronous circuits are also fairly difficult to design and debug. They can be sensitive to physical factors such as excessive heat or supply voltage drops. Those might negatively affect performance. And since synchronous design has been so predominant, really the entire time circuitry's been around, there are a few people trained to actually develop asynchronous circuits. After viewing both the advantages and disadvantages of the asynchronous design, is it important to ask, is it actually worth designing these asynchronous circuits? The simple answer is, in certain scenarios, yes, it is. Due to the fact that most of the disadvantages fall into two major categories, that the improved performance is actually not as much as previously thought, and the fact that it could take a lot of money to actually design these circuits, mainly due to the fact that few people are actually trained in designing them, it just becomes a simple matter of making sure that the benefits outweigh the cost. The key to doing this is knowing which synchronous circuits we should replace with asynchronous ones. In essence, we want to replace smaller and frequently used circuits with asynchronous ones, because this way they will be used enough that the small improvement in performance will eventually build up to a much larger in the long run. And at the same time, it will be simple enough that people can design it fairly easily, and because making a fully asynchronous CPU is just not optimal with the current technology. Despite some of the disadvantages, asynchronous circuits are used in a couple of things these days. One example is wearable computers. Essentially, wearable computers have been applied to areas such as behavior modeling, health monitoring systems, information technologies, and media development. Government organizations, military, and health professionals have all incorporated wearable computers into their daily operations. These computers are used for any applications that require computational support while one's hands, voice, eyes, or attention are actively engaged with the physical environment. And these, along with pagers, often used by emergency personnel and the like, they really represent the system that we introduced in the last section of Is It Worth It? Because they only use really small circuits that are being used frequently to make sure that the benefit is outweighing the cost. And infrared communication receivers, it's a very similar type of system. They are peripherals to normal computation devices, so they already use inherently small circuitry, pretty simple, that but it can be used quite frequently depending on how much they're being used in their given applications. It is easy to see that the potential is there for this technology. In an increasingly mobile world, the energy saving alone could be worth the effort of integrating more and more asynchronous components into technology. Obviously, solutions do need to be obtained for the disadvantages in order to truly unlock the design's full potential. Some areas being looked into include pipelining the asynchronous circuits in order to further improve the performance gap from synchronous circuits, and developing new ways to prevent slowdown from overheating. With technology becoming more and more mobile, and so much importance being put on speed of technology, now is the perfect time to begin fixing the problems with asynchronous systems to create better technology. Provided are the sources that we use to obtain the information used in this report. If you'd like any additional information regarding asynchronous circuits, CPUs, or the asynchronous system in general, please check out these references.